Okay, great. So why don't we start? Welcome everybody. It's a pleasure today to have Ashkan Jasur from MIT CSEL, who's going to give a talk on moment and some of course-based semi-definite programming for chance constraint optimization.
Okay, let's get started. Hello, everyone. So this talk is about convex relaxations for chance optimization problems. And this is how I define chance optimization problems. In chance optimization, we are looking for design parameters to maximize the probability of success. And this success comes from the nature of the problem. In general, success is a set defined in terms of design parameters and also probabilistic uncertainties. To see this, let X be our design parameters. Omegas are our uncertain parameters with given probability distributions, or in general, with given probability measures. Also, PIs are polynomials in X and omegas, and GIs are polynomials in terms of X. Then chance optimization reads as follows. We are looking for design parameters X to maximize the probability of success defined in terms of level sets of polynomial PIs. So success set is nothing but a semi-algebraic set defined in terms of the X and the uncertain parameters omega. So we are looking to maximize this probability with respect to some deterministic constraints in terms of design parameters X. For example, let's look at this simple example. In this example, we are given 4 assets with uncertain rate of return denoted by omega i's. Omega i's are probabilistic with some given probability distributions. Xi's are invested money in each asset. And the success is defined as achieving a return higher than predefined value R star. So we can calculate this return in terms of design parameters Xi's and also uncertain parameters omega i's. So our success set is this semi-algebraic set defined by level sets of these given polynomials. And also, we want to make sure that the total investment is bounded by some predefined value X star. So chance optimization formulation of this problem reads as here. We are looking for invested monies to maximize the probability that return money is greater than predefined value R star. This semi-algebraic set with respect to this deterministic constraint in terms of the design parameters. So this is how I define chance optimization. Now, in chance constraint version, instead of maximizing the probability of success, we just want to make sure that probability of success is greater than predefined value 1 minus delta, where delta is an acceptable risk level. So in chance constraint, we just minimize or maximize some deterministic objective function with respect to this probabilistic constraints. Now, these optimizations, chance optimization and chance constraint version, are in general non-convex and computationally hard to solve. And one reason for this is that in these problems, we need to deal with probabilities, and this involves dealing with multivariate integrals with respect to the probability distributions over, in general, a non-convex set. Such integral doesn't have any analytical solution, so in general, it's hard to deal with. Existing methods to address chance optimization problems are mainly based on sampling-based approach, like Monte Carlo sampling techniques, or they only address particular class of constraints and uncertainties. For example, linear chance constraint with Gaussian uncertainties. In this talk, we are going to develop an approach to address a general class of chance optimization problems. And for this, we look for convex relaxations in the form of semi-definite programs. And to obtain such STPs, I'm going to leverage on theory of measured moments, theory of sum of squares polynomials, and also duality of conic programs. So what are the assumptions in this approach? So we have two main assumptions. First, all of the functions and constraints inside the chance optimization and chance constraint version are polynomial functions. And also, all the sets are compact, or more precisely, all the sets are Archimedean. And we can easily satisfy this condition by adding a polynomial of this form, this redundant polynomial. By adding this polynomial into definition of the sets, we can satisfy the Archimedean condition. For more information on Archimedean, you can look at this reference here. So before I get into details, these are the steps we need to take to find the convex relaxations and solve the chance optimization. In the first step, to solve this chance optimization, I'm going to treat design variable x as a random variable. So by doing so, instead of looking for x, I am going to look for its probability distribution. By doing so, I am going to obtain infinite dimensional linear program in terms of measures. In the next step, instead of looking for measures, I'm going to look for the moment sequence of the measures. And moments are nothing but expected value of the powers of the random variable x. By doing so, I'm going to get infinite dimensional semi-definite programs in terms of the moments. And to solve such infinite dimensional STP, in the next step, I'm going to truncate the matrices and only look for truncate moments. And this is going to give us a finite moment STPs. And at the end, we are going to extract the solution of the original chance optimization by looking at the moments that we obtained by solving the finite moment STPs. So these are the steps to solve chance optimization. Now for chance constraint problem. To solve this given chance constraint optimization, I am going to look at the dual optimization of the finite moment STP of the chance optimization. By doing so, I'm going to get a sum of squares optimization whose solution approximates the feasible set of chance constraint optimization. And what is this feasible set? This is a set of all design parameters whose probability of success is greater than 1 minus delta. I am going to replace this chance constraint with the deterministic constraints in terms of polynomial PCC. This polynomial is the solution of sum of squares problems. By doing so, I'm going to obtain both inner and outer approximation of the chance constraint set. And then by obtaining this set, I can turn this chance constraint problem into a deterministic optimization problem with respect to new deterministic feasible set for the problem. So these are the overall steps that we need to take. So let's look at these steps in more detail. So any questions so far? So first, chance optimization problems. So in chance optimization problem, as I said, we are looking for design parameters x to maximize the probability of success. So in the first step, I'm going to treat these design variables as a random variable. So it means that instead of looking for the design parameters, I'm going to look for its probability measure. By doing so, I'm going to get two sets of probability measure. First, unknown probability measures of design parameters mu x. Next, given probability measures of uncertainties, denoted by measure mu omega. So measure mu x is unknown. It is assigned to our design parameters, and measure mu omega is given. Now I am going to obtain the equivalent optimization in terms of measures mu x and measure mu omega. And for this, first I'm going to define two sets. First set K, which is our success set defined in terms of the polynomials in x and omega. This set is in the space of the x and omega. And next, the set chi, which is our feasible set of the chance optimization defined in the space of x. By defining these two sets, the equivalent optimization in measure space reads as follows. In this optimization, I'm looking for measure mu x assigned unknown measures to design parameters x, and also a slack measure mu. Measure mu is supported inside the set K, our success set defined in the space of the x and omega, and measure mu x is supported inside our feasible set chi. And measure mu is upper bounded by the joint probability measure of the x and omega. So this cross product represents the joint probability measure of the x and omega. And in this optimization, we are trying to maximize the volume of the stack measure mu. This is infinite dimensional linear program in terms of the measures. And to explain this optimization, let's look at this simple example. So in this example, this is our success set K defined in the space of x and omega. And now in the measure space, we have given probability measure of the uncertainty omega. So here I am plotting its PDF, a probability density function of the omega. And also we have unknown probability measure assigned to our design parameter x. So given probability measure omega, unknown probability measure design parameters. And now suppose that this measure mu x is also given. So given probability measures mu omega and probability measure of the design variable x, the goal is to find the probability of the success in terms of the measures, given measures mu x and measure mu omega. And for this, from the definition of the probability, we need to deal with this integral with respect to the joint probability distribution of the x and omega, plotted as here, the joint distribution, over the set K, which is our success set defined in the space of the x and omega. So as I mentioned earlier, such integral is challenging to solve. So to be able to solve this multivariate integral, I am going to introduce a slack measure mu. This new measure mu is supported inside the set K, our success set, as shown here. And also measure mu is equal to joint measure of x and omega inside the set K. So if I can find such measure mu, then probability of success is nothing but the volume of this stack measure mu. And why this new integral is easier to handle compared to the original integral of the probabilities? Because this integral is nothing but the zero order moment of the measure mu. So it means that if I can find such measure with these properties, I can look for its zero order moments and find the probability of success. And how should I find this measure? By solving such optimization. Look for measure mu. Measure mu is supported inside the set K, our success set. It is upper bounded by the joint measure of x and omega. And in this optimization, we are trying to maximize the volume of this measure. So we are going to maximize its volume until it hits the upper bound measure, this joint measure here. So by doing so, I can then look for its zero order moments and find the probability of the success. Now, I assume that the measure mu x is given. Now that measure mu x is unknown, to maximize the probability of success, we need to, at the same time, look for measure mu x and also stack measure mu. And for this, I just need to add the new variables to our optimization. So we are going to look for stack measure mu and also measure mu x assigned to design parameters with the same cost function and constraints in terms of the mu and also in terms of additional constraints. Mu x is a probability measure and it is supported inside the feasible set of the chance optimization. And this results in our equivalent optimization in terms of the measures. So this is, as I said, this is infinite dimensional LP, and the following theory holds true. The original chance optimization and this measure LP are equivalent in the following senses. Optimal values are same. Next, If mu star is an optimal solution of the measure LP, then any point x star is inside the support of this measure mu star is going to be an optimal solution of the original chance optimization. And next, if x star is a unique global optimal solution of the original chance optimization, then Dirac measure defined on top of this point x star as shown here. This Dirac measure is going to be a unique optimal solution of our measure LP. And if we have multiple global solutions for our chance optimization, we are going to observe multiple Dirac measures in the measure space defined on top of the global solutions of the original chance optimization. So what it means that to extract the solution of the original chance optimization, I just need to look at the support, these points of the delta distributions. And I'm going to do this later by looking at the moments sequence of these Dirac measures to obtain the supports and as a result to obtain the solution of the original chance optimization problem. So this is the result for step 1. So we reformulate the problem in terms of measures, we obtain infinite dimensional linear program. Now to solve such infinite dimensional linear program, instead of looking for measures, I am going to look for the moment sequence of the measures. And for this, we need to write the objective function and constraints of the measure LP in terms of the moments of the measures. And for this, I'm going to use this necessary and sufficient moment conditions. Let K be a semi-algebraic set defined by polynomial Ji's. Then sequence Y has a representing measure with supports inside the set K if and only if we satisfy the following linear matrix inequality in terms of moment and localizing matrices. So moment matrix is a symmetric matrix defined in terms of the moments Y, and localizing matrix is a symmetric matrix defined in terms of the moments and also coefficients of the polynomials that describes our set K. And these are two simple examples for the moment matrices. For example, here we have a moment matrix constructed by the moments up to order 4. And here we have a localizing matrix constructed by the information of the moments up to order 4 and also given polynomials. Now, by using this condition, instead of looking for measures supported inside K, I can simply look for a sequence Y that satisfies these LMIs in terms of the moment and localizing matrices. So to obtain a optimization in terms of moments in our measure LP, I'm going to replace all constraints in terms of the moments. So constraints for our mu x is replaced by the moment and localizing matrix in terms of the sequence yx. Yx is the moment sequence of the measure mu x. Similarly, I do the same for measure mu. I replace these constraints with the moment and localizing matrix in terms of the sequence y that represents the moment sequence of the measure mu, and same goes for the upper bound measure. We replace this condition in terms of the moments and the moment matrix and the moments of the distributions. By doing so, by replacing these constraints, we are going to get such semi-definite programs. In this semi-definite program, I'm looking for sequence y, moment sequence of the measure mu, and also sequence yx, moment sequence of the measure mu x, with respect to these linear matrix inequality. Here, so we are seeing an infinite dimensional semi-definite program because to construct these matrices, I need the information of the all moments of the distributions, moments up to order infinity. And note that this semi-definite program is equivalent to the measure LP. So as a result, this is equivalent to our original chance optimization. Now, to solve this infinite dimensional semi-definite programs, in the next step, I am going to truncate the matrices and only look for the moments up to order 2D. This results in this new finite moment STP, where I'm just looking for the moments up to order 2D. then following theorem holds true. We can show that optimal solution of the finite moment STP converges to the optimal solution of the original infinite dimensional STP as we increase the D, the relaxation order D. As I look at the higher order moments, as I increase D, the solution of the finite STP is going to converge to the solution of the original STP. And also for any finite relaxation order D, the objective function of the finite STP is going to be an upper bound of the optimal objective function of the original chance optimization. So it means that this optimal function of the finite STP is always an upper bound on the probability of success. And as we increase the D, as we increase the relaxation order, this upper bound is going to converge to the true probability of success. So this is the results for the finite STP. So to solve such chance optimization, I'm going to solve this finite dimensional moment STPs in terms of the moments of the measures. Now to extract the solution, so once we obtain the moment sequence Yx, we are going to identify the Dirac measures by looking at the measures of mu x. And then we are going to extract the solution of the original chance optimization by looking at the support of the Dirac measures. And for this, I'm going to use this property of the Dirac measures. Sequence Y is the moment sequence of a Dirac measure if and only if it satisfies this rank condition. If rank of moment matrix is 1, so we can claim that that sequence Y represents a Dirac measure. So we are going to obtain a moment sequence Yx, then we are going to check this rank condition. If this is satisfied, so it means that those moment sequence represents a delta distribution, and then we can simply look at its expected value or its first moment to extract the support. So mean or first order moments of the delta distribution is nothing but its support, which is in our case, this point represents the solution of the original chance optimization. And similarly, if that moment sequence satisfies this rank condition, rank of moment matrix of order D equals to rank of moment matrix of order D minus 1 equals to R. If we satisfy this condition, it means that this sequence of the moments represents R delta distributions in the moment space. So we can extract R global optimal solution for original chance optimization. And to extract the support of these delta distribution, we need to solve a linear algebra that relies on a moment matrix factorization. And for more information on this algorithm, you can look at this algorithm. So this is how I'm going to extract the support or the solution of the original chance optimization. So this summarizes the chance optimization part. To solve this chance optimization, where we are looking for X to maximize the probability of success, we are going to construct a finite dimensional moment STP. We are looking for a sequence of the moments. So for any relaxation order, the objective function that we get is always upper bound of the true probability of success. And as we increase the relaxation order, this probability, this objective function is going to converge to the true probability of success. And also, if obtained sequence of the moments for design parameters denoted by Yx, if this satisfies the rank condition, we are going to extract the solution of the original chance optimization by solving the linear algebra that I just explained. Otherwise, we need to increase D and solve another STP. So when we satisfy this rank condition, we can extract, otherwise we need to solve the higher order semi-definite programs. Any questions so far? Okay, so let's look at this simple example. So here I'm looking for design parameter x to maximize the probability of success described by this polynomial in x and omega. Omega is uncertain parameter with a uniform probability distribution. This is our success set in the space of x and omega. This is obtained moment SDP. I'm using moments up to order 4 to construct the moment and localizing matrix. This is the solution that I obtained. The sequence of the moments for measure mu. So the zero order moment shows the upper bound of probability of success for this problem. And this is obtained sequence of the moments for measure mu x. I check the rank of the moment matrix associated to this moment sequence. The rank is numerically 1, so it means that we can approximate this distribution by delta distribution. So as a result, we are going to approximate the solution of the original chance optimization by the first order moments of this sequence, which is 0.5. And this happens to be an exact solution of the original chance optimization. And this is how upper bound probability, the zero order moments of this sequence decreases as I increase the relaxation order. As we decrease the relaxation order, as we look at the higher order moments, this probability decreases and converges to the true probability of success of the problem. And as another example, so here.
Sorry, on the previous example, I was just a bit confused. It seemed like the first order relaxation was tight based on the rank test.
It's not the first, sorry, it's not the first order relaxation. So
oh, it's the fourth order, sorry.
Yeah, fourth order, yeah.
Thank you.
Yeah, so in the second example, so this is our success set, which is a non-convex in the space of the x and omega described by this polynomial. Omega is a uniform distribution. This is the sequence of the moments that I get. So moments up to order 5. I check the rank of the moment matrices. The rank of moment matrix is 2. So it means that we can extract 2 global optimal solution for the original chance optimization. So by solving the linear algebra in terms of the moments, I exactly recover the original solutions as shown here. These are the original solutions. These are the exact solution of the original chance optimization problems. So these are my results for chance optimization. And now in the next step, I am going to look at the dual optimization. I'm going to obtain the dual optimization of the finite moment SDP. And for this, simply I'm going to apply the standard results of the duality of conic program. By doing so, this is the dual SDP that we are going to get. Note that the first finite moment SDP is looking for moments up to order 2D. This obtained dual SDP is looking for polynomials up to order 2D. In the dual SDP, we are looking for scalar beta and also polynomial W in x and omega. This polynomial and beta are non-negative. The polynomial is greater than 1 inside our success set K, and also beta is upper bound of this integral. And this integral is nothing but the expected value of the obtained polynomial with respect to the probability distributions of the uncertainty. And note that these are non-negativity conditions of the polynomials, and we can relax these constraints into sum of squares condition, and as a result, we can obtain a sum of squares optimization. And now let's explain this dual SDP. For this, so for a given design variable x star, this obtained polynomial W is going to be an upper bound polynomial approximation of the indicator function of the success set for given design parameter x star. And why is that? Because W is greater than 1 inside the set, and it is non-negative. We are minimizing beta. Beta is the upper bound of this integral. So by doing so, we are pushing this polynomial toward the indicator function of our success set. So W is going to be an polynomial approximation, an upper bound approximation of the indicator function of our success set for given design parameters x star. And this is exactly what we need to calculate the probability. Probability, expected value of indicator function of a set is nothing but the probability of that set. So as a result, expected value of this polynomial approximation of the indicator function, as here, is going to show us a upper bound of probability of success for given design parameters x star. And in general, this expected value is a function of x, and for any given x, this expected value represents a upper bound on the probability of success for given this design parameters x. So it means that to maximize the probability of success, we just need to look at the maximum point of this function, this expected value function. And to see this, let's look at the previous examples. This is the examples that we use the moment STP to obtain the solution. Now, this is the solution of the sum of the squares optimization. This is polynomial W in the space of x and omega. This is the solution of the sum of squares. This polynomial is greater than 1 inside the success set K, and it is non-negative in this space. And this is our expected value of W star, this integral, that represents upper bound of the probability of success. Now, if you look at the maximum of this function, which is equal to the beta star, and beta star is the optimal objective function of the sum of squares formulation. This maximum represents the upper bound on the maximum of the probability of success. And if you look at this point, x star, this represents the solution of the original chance optimization. This is the results we exactly obtained by solving the moment STP. So by just looking at the maximum point of this function, we can extract the solution of the original chance optimization. And moreover, if we choose different points in the space of the design parameters, we are going to obtain a probability of success, upper bound on the probability of success for this chosen design parameters. So what does it mean? So it means that since this function is an upper bound of the probability of success, if you look at its level sets, set of points for which this polynomial is greater than 1 minus delta, this is going to be outer approximation of our original chance constraint set. This set is an outer approximation of the set of design parameters whose probability of success is greater than 1 minus delta. And this is how I extract the chance constraint set by looking at the dual STP and solving the sum of the squares optimization. And now, before I provide more details, I'm going to modify our SOS optimization. Now that we know in the SOS optimization, we need to look for some indicator function, I can improve the results by directly minimizing the integral of the polynomial W. So for this, I drop this beta and I move this integral to the objective function. And this time I try to minimize this integral both in x and omega space with respect to the same constraint. By doing so, I can get a tighter, better approximation of the indicator function. And as a result, we are going to get a tighter outer approximation of the chance constraint set. For example, so this is the results for the previous example. The first function is a expected value of the W, which I obtained this by solving the sum of squares for the relaxation order of 5. This is a polynomial of order 5. The second function is obtained by solving a SOS for relaxation order of 10. And this dashed line is a true probability of success. So to obtain this for each design parameter x, I sampled the uncertainties and I used Monte Carlo to obtain the true probability of success for each design parameters. So as we see, these obtained functions by solving SOS always are upper bound of the true probability of success. Now I'm going to construct a chance constraint set. So this is a true chance constraint set of all design parameters whose probability of success is greater than 1 minus delta. Now, the outer approximation is as here, set of design parameters x for which this function is greater than 1 minus delta. So this super level set is going to give us the outer approximation of the chance constraint of the original solution. We can also obtain, so this is outer approximation. I can also obtain inner approximation. And for this, we can apply same methodology to the complement set, which is nothing but the failure set. So for this, I'm going to define chance constraints in terms of the failure set of design parameters whose probability of failure is less than delta, apply the same methodology and solve the SOS and obtain the outer approximation of the set. And now this outer approximation of the failure set is going to represent the inner approximation of the chance constraint in terms of the probability of success. So by doing so, I can obtain the inner approximation. For example, in this example, so this is the results that obtained by solving the sum of squares optimization. So the polynomial W bar is 1 inside the complement set. And it is less than 1 inside the success set K. And this is its expected value. And now if you look at its delta sublevel set, a set of points for which this polynomial is less than delta is going to be an inner approximation of the chance constraint, a set of points for which probability of success is greater than 1 minus delta. So this is how I obtained the inner approximation of the chance constraint set. So this summarizes the results for chance constraint optimization. To solve such chance constraint optimization, where we are trying to make sure that probability of success is greater than 1 minus delta, we construct the sum of squares optimization by looking at the dual finite STPs of the chance optimization. So by solving these SOS, we are going to get the polynomials, and the level sets of these polynomials is going to approximate the inner and outer approximations of the true chance optimization, chance constraint optimization. Also, as we increase the D, as we increase the order of the polynomials, these sets are going to converge to the true sets. And also note that, so if I only solve one SOS and obtain this polynomial, I can construct the chance constraint for different values of the delta. So by obtaining this chance constraint set, then I can turn this chance constraint optimization into a deterministic optimization in terms of this new deterministic chance constraint set. And note that we can also add additional constraints. For example, in SOS optimization, I can add some SOS convexity constraint to make sure that this feasible set is convex. So by doing so, if the objective function is convex, then the total optimization is going to be a convex optimization, and we can solve it efficiently. So this is the almost end of my talk. For more information, for more details, for examples, for codes, and also more precisely, and more importantly, for the applications in uncertain dynamical system and also in robotics, please look at this website. That it has my lecture notes that I have prepared for the course that I have recently taught at MIT. It's called Discovery and Robust Nonlinear Planning. And also you can look for my related papers at here. So I'm ready to take any questions.
Thank you for a nice talk. Questions for Ashkan?
I have a question. So I think you hinted a little bit during your talk about the choosing some particular parameters. And there's a, it's very popular to use these sampling methods in chance constraint optimization. Can you comment on how to mix the two properly, let's say, or improve the one with the other?
So I didn't get the question. So you mean I use the sampling-based techniques methods to improve my results, or?
Well, I mean, possibly.
So let's put it this way. So all sampling methods, so they gives probabilistic guarantees. So we cannot guarantee the solution. The solution that I'm going to get, it's not guaranteed that the probability of success is greater than predefined value 1 minus delta. But in this provided approach, we can guarantee that the obtained solution is always going to meet our chance constraints.
Mm-hmm.
Does that answer your question?
I think so, yeah. Mm-hmm.
So can you give a sense of, kind of, again, perhaps you don't obtain, it's true that, kind of, if you do sampling type methods, you don't get somehow deterministic guarantees, but you get guarantees with high probability. And if this probability is like 1 in whatever, 10 to the minus 12, whatever, then, somehow. Yeah. Can you give a sense of, kind of, in terms of computational effort, kind of how these things compare?
Yeah, compared to the Monte Carlo sampling. So when we are dealing with a large scale problem, so actually the both techniques are not going to scale, because so as you know, we need to deal with the large scale semi-definite program, and it's always pain to deal with such large STPs. But which was so based on my experiments, so lower order STPs always is scaled better compared to the sampling based techniques. But this is for sure.
But for the same quality of the bounds, because one could think that, I mean, in a sense, these things rely on approximating indicator functions with polynomials, and and that's not a very
it's approximation.
I mean, they don't approximate. I mean,
that's right.
They don't. Indicator functions don't want to be approximated by polynomials, right? Like,
so that's it. So yeah, Monte Carlo techniques is going to give us a more precise solution, but so in terms of the design parameters. But so as I said, with no guarantees. So the point of this technique is that we can guarantee the solution. And if we have efficient STP solvers, then we can, of course, outperform the sampling-based techniques.
Mm-hmm.
And yeah, to deal with a large STPs, I have also started looking at the Breuer-Montero's type STP solvers that look for the low rank solution. And here I have a rank condition. In the moment space, I'm looking for delta distribution, and we know that they should satisfy the rank condition. And I hope this Breuer-Montero solvers help me to solve a large scale semi-definite programs, but I don't have the results yet.
Any other questions or comments?
I have a quick question. So one avenue to mix maybe sampling and this thing is, I assume you are assuming that you know the distribution of W and you know the moments exactly, but now assume you don't have in closed form the moments of the distributions of W, but you have samples of W. Can you give finite sample guarantees by using samples from W, but doing something with polynomials for your design parameter?
Yeah, so you mean that, my assumption was that I have an exact moment information of the uncertainties. In your case, the moment itself are uncertain. So for that case, so I didn't talk about, so there's a distributionally robust extension to this work. In that case, we assume that the distributions of the uncertainties are also uncertain. For example, I have a Gaussian distribution with uncertain mean and covariance. So by this, I can construct a distributionally robust set for my moments. And by doing so, yeah, I can give guarantees, but it needs extra extensions. Does that answer your question?
Thank you.
Last chance for a question. Okay, if we don't have any more questions, then we'll thank the speaker again, at least virtually. Yeah, and I guess we'll see you next week. Thank you.
Thank you.
Bye.